let's review again. So this is an interface for BST. And since the object that we put in BST, it has to be implemented. The method has to have compare to being implemented in the object. So that's why in our generate here, parameterize here, we have to put t extends comparable because compare has to compare to. Then we make sure that the object that uses BST has to implement compare to by doing this. And this concept we call generic programming. We have in order, pre-order, and post-order. So these are constant to specify the type of traversals. Method is empty, size contains, remove, get, add, reset, and get text. Right, just like what we have done before in the list. So at the application level, we said BST ADT is very similar to our sorted list. And we can look at applications like BST later in the application. But let's see how we're going to implement it. So we can see that node. This is just like the doubly linked list. That one node has front and back, right? But this one is going to be left and right instead. Okay, which is different. It's not going back and going straight. It's just going down. Then we create a node with info with left and right. And we said BST class is going to same object has to be extends compatible and implements the BST interface. And we're going to create a node to point at root of the tree. Just like what we have in the linked list, we have list, right? This is called tree or root. And then we need to have like this one. It happened to make it to share when they do contains. They just say set file to true, right? Or when you before you remove, you have to call contains. Then they're pretty much sharing the file attributes here. Then we can remove. If you look at the interface of contains, you can return true too. But in previous list, they didn't do return true. You can just share this. They just do one. If you look at it in chapter 7. But this is fine. You can make it as the default to the class. It's just based on your design. It's not necessary to include it. And let's look at traversals. So once we travels, then we have in order, pre-order, and post-order. Right. Then we want to create a list to store this. So that list happen to use the queue. Okay. And linked list queue. Tree list. Constructor. First, when you instantiate BST, then root is equal to no. Tree is empty. Is empty. Root equals to no, right? That is empty. Now, let's look at, we start to implement the methods, right? We look at, should we use iteration or recursion? And we look at trees are inherently recursive, because tree consists of subtrees and trees also subtrees. So we're going to use recursive, right, approach. We can also use iterative approach too for the size, because that should be not too difficult. But when you implement with iterative, it may be more complicated, so we may have to use recursion to help. So let's look at an example of, let's say we want to implement the size of the tree. How would we use recursive approach? So we can create a method named public int size, and this will return a number of elements in the BST. Return. So we're going to create another method called recursive size to return the number of nodes in the subtree. And we pass the root to it. So you may note that the number of nodes in a tree is the number of nodes in left subtree plus number of nodes in right subtree and plus the root. So let's look at the algorithms for the recursive size. This is the first version. So this method will return an int, which is the number of nodes for the tree that we pass in. If tree.getLeft is null and tree.getRight is null, that means we return 1. That's the best case, right? Because you get to the left. Else, you recursively pass in tree.getLeft node plus recursively size pass in tree.getRight node plus 1. Now, when we look at this, we said this program will crash when tree is null. Because if the tree is empty, you try to say if tree.getLeft. This is actually an error right away. You cannot say tree.getLeft right here because it is null. Then we have to revise this. If tree.getLeft is null and tree.getRight is null, returns 1. Else, if tree.getLeft is null, return recursively getRight plus 1. .getRight is null, return recursively size tree.getLeft plus 1. Else, return both plus 1. This still causes errors, but I said if tree.getLeft. If tree is empty, it still causes errors. Then we revise that if tree is null, return 0. Okay, that makes sense, it's empty, right? Size is 0. Now, else if tree.getLeft is null and tree.getRight is null, return 1. That makes sense, it's only 1. Then we do the same getLeft. If getLeft is null, then we just do recursive to the getRight plus 1. As well as if getRight is null, just return the left node, right, plus 1. We do plus 1 because the root itself at the end. So this code works, but can be simplified. There are two best cases. We can collapse into one. No need to make the leaf node a special case. So this is the leaf node, right? Return 1. We can say, instead of this, we can say if tree is null, return 0. Else, you can just make recursive size tree.getLeft plus recursive size tree.getRight plus 1. Because if these are all 0, then it's going to do returns 1. And they also support the other cases. So this one works in simple. You may say that this textbook tries to help you in the term of designing approach implementation level, because once, if you didn't see this at the end, it's very difficult to get to this point. When they start to say, first you have to install in some code, revise the code. This one being revised 4 times. Always, first thing, check for the empty tree first. And leaf nodes do not need to be treated as separate cases. It could be just one. Yeah. Then we start to implement it in Java. Recursive size. So that is recursive version. Now if you look at the iterative version, how would you do that? Alright, so we said we use stack to hold nodes we have encountered but not yet processed. We must be careful that we process each node in the tree exactly once. By following the rules, process a node immediately after removing it from the stack. Do not process nodes at any other time. Once a node is removed from the stack, do not push it back on the stack. So we create a stack to hold the nodes that we have to process, right? Let's look at algorithms. This is pretty much a method returns inside. Set count to 0. We need a counter. If the tree is not empty, that's the first thing to check, right? Then we start to do this. Otherwise, return count as 0. Now, if it's not empty, we get into the if statement. We create a stack, and we push the root of the tree onto the stack, while the stack is not empty. Set the current node to top of stack, and we pop the stack. Increment the count. Now, if current node has a left child, then push it back onto the stack. And if current node has a right child, then push back onto the stack. And start to loop back if the stack is empty or not. Then keep doing the same. Set current node to the top and pop it out, because we resetting it, right? And pop it out when we keep tracking on the count. And check that current node again if it has left child or not. If not, there are leaves. Then we're done.